This is problem 97. A 60 kilogram student lifts herself from rest to a speed of 1.5 meters per second in 2.1 seconds. The chair has a mass of 35 kilograms. Starting from rest, speeding up gives you a motion diagram like this, where the velocity vectors are getting longer and the acceleration is pointed upwards. We're going to put the origin at the initial position for the student and the chair. The student and the chair are moving together. And event 1 is when the student begins to lift herself, and event 2 is 2.1 seconds later. We draw a velocity versus time graph, starting from rest, ending at a positive velocity. The area is the area of a triangle. That gives us 1.575 meters. You can round it to put it in your table, so let's make that 1.58 meters. And the acceleration is change in velocity over change in time. That gives us 0.714 meters per second squared. Now that we have the acceleration, we can use Newton's second law. Do a free body diagram for the student and the chair. You have force of gravity acting downward on the student and on the chair. That's mass times 9.8. The student exerts a force downward on the chair exerts a force upward on the student. Those forces are equal in magnitude and opposite in direction. The student is touching the rope exerts a force upward on the student and upward on the chair. For the student, we have force of chair on student plus T, those are going upwards, minus the force of gravity, which is 588 newtons, is equal to the mass of the student times the acceleration, that's 42.86, that's equation 1. For the chair, tension pointing upward minus force of student on chair minus 343, which is the force of gravity, is mass of chair times acceleration, that's 25.0. Add equation 1 and 2 together, and you get T plus T is 2T, force of chair on student minus force of student on chair. That's the magnitude, because we already included the direction when we put a negative sign here and positive sign here, so those cancel out. Minus 588 minus 343 is minus 931. That is the force of gravity for the student and the chair together. This is the mass times the acceleration for the student and the chair together, because that was this times this. 2T is what you would get if you did the free body diagram for the student and the chair. So this would be the total force of gravity acting downwards for the student and the chair, which is the 931. Then you'd have tension acting up here and here, and mass times acceleration would be the total mass times the acceleration. So this is what you would get. That's what you would get if you did the free body diagram for the student and the chair together. Then you could solve for the tension. But in order to find the force that the student exerts on the chair and the force that the chair exerts on the student, you either have to use equation 1, which comes from the free body diagram for the student, or the equation 2, which comes from the free body diagram for the chair. So you can do this if you're just looking for the tension in the rope, but in order to find this last force, we need an additional free body diagram. That gives us 131.43. You can round both of these, but I didn't want to round this one too soon, because then it would look funny. If you do, you could use either this equation or this equation to solve for it, but if you don't round it, this is what you would get for both equations. Okay, so that concludes 97.